Okay, in this video we're finally gonna start to do something with the chain rule after we review all of the rules for the derivatives. And the chain rule, the way I see it, it's pretty much two things. It's just one is matching the rules, which is you're matching the expression that you need to take the derivative of and match them with the rules that we reviewed before, which is like this. You know, the rules that take the derivative of constant is 0 and take the derivative of e to the power is e to the power, like this. Just match the expression with those rules. And the second thing that I think about the chain rule is it's like when we are calculating something, it's order of operation. It's the order of operation. Yeah, one way to take the chain rule, to use the chain rule, is just take the derivative of the most outside things and then do it step by step, going toward the inside until you take the derivative of the last thing, which is I called it the easiest thing to take the derivative of. So this is the two things, yeah, matching the rules and order of operation. Okay, what does those things mean? Well, it won't mean anything until we do an example of that, so let's do an example. Let's pick an easy one. Okay, and I'll find the one that is also in your book so you can take a look at it at home. Okay, so let's do this is come from the book 3.6. Yep, 3.6, and let's do number 9. Let's do number 9. Okay, the question is, we want to find y prime, and the function is this, 2x plus 1, right? So to find y prime, we know that the derivative of y is y prime, and you know, we're just taking the derivative of both sides. Pretty simple. Yeah, it's the same thing that you've been doing in implicit differentiation. You always take the derivative of both sides. So you see that? So this is y prime, and this one, oh wait, actually the question is 2x plus 1 to the 5th power. Okay, first thing, remember what I said? First thing is to match this expression here with all the rules that you know, and see if you can find a rule for this. So this is something to a power, right? Something to a power. So now let's look at the roots. We have constant, we have derivative of this, and now we find that there's a rule for something to the power. So now let's use this rule to solve for this. So we know that the derivative of something to the power, it's just bring down the power times that something to the power minus 1. So which that will be the power 4 to the 4th. But are we done yet? Well, no, we're not done, because we have only taken the derivative of the most outside part. The most outside part. And remember what I said, the order of operation? We are going from the outside toward the inside. So if we only take the derivative of the first level, so now we just move in. After we take the derivative of something to the power, this power is gone. Like, we're not taking the derivative of this power anymore. So now when we look back inside that something, there is 2x plus 1. Now 2x plus 1, you may want to look at the rules again to take the derivative of this, but I'm pretty sure you're smart enough to pretty quickly to find the derivative of 2x plus 1. And the derivative of 2x plus 1, which is just 2, because the derivative of 1 is 0, right? So what happened to this 2? Well, this 2, we always just multiply it back to the derivative that you just got from the previous level. So now after that, you try to see, like you ask, okay, am I done this time? The question is yes, because you see this 2x plus 1, that is the part of this expression that's the easiest to take the derivative of. That's the goal, because you want to move from the outside toward the inside. And once you reach to the point, like reach to a part that is like pretty easy to take the derivative, then you're done. So the answer to this question, the derivative of this expression, the original question was this: 2x plus 1 to the 5th power. So the derivative of this is this: 10 times 2x plus 1 to the 4th power. Yep. So but there's another way that you can do. They can take the chain rule. Another way that I found kind of helpful is this. So we do this question again. Okay, so we're still on the same question, 3.6, number 9. And another way to deal with this question is you create this thing here. You still kind of want to you want to break this expression apart. Break it apart. You see I'm drawing those parentheses here. First thing first, remember when I was solving this question previously, I try to take the derivative, I try to do it from the outside and then toward the inside, right? But this question, you look at the inside first. You will look at the inside first. So what you want to do is you want to find the most inside parts of this expression. The most inside part of this expression. In this case, the most inside part, which is 2x plus 1. That's the one that you can take the derivative right away. Take the derivative right away. Because you know anything that outside 2x plus 1 it's 2x plus 1 to the 5th. So you know that it's not something that you can take it right away, because you have to use chain rule for that, right? So this is the one that's the most simplest part of this expression. Now you will just go outward. Now the second one that you will look at, okay, what is the thing that outside of 2x plus 1? Okay, right? There is nothing beside to the 5th power, so just something to the 5th power, right? Something to the 5th power. Or you can write it as, just write it, the entire thing, 2x plus 1 to the 5th. Okay, so after you break down the problem like this, you start from the most inside and then you just will going out. But for this question, this problem will just break down into two parts. So after you break down the question, what you can do is just to take the derivative of each part, and multiply them together. It's like this. See that the derivative of this is just 2, and the derivative of this is just 5th and 2x plus 1 to the 4th. And if you multiply them together, it will give you the same answer as we got just now. Now I know now this sounds really confusing, but we're gonna do another example and see what happens. Okay. Now let's try another example from the book. I think this may be number 11, also from 3.6. 3.6, number 11. It may be number 13, I'm not really sure. I think it's number 11. So, but it's an odd problem, so you can look at the solution menu for this. You can check the answer. Okay, so the problem is y equal 1 minus 1 over, wow, you know what, I rewrote it, the problem, but okay, it was x over 7 and to the negative 7 power. Okay, remember, first thing, we're gonna use two ways to solve this again. We're gonna use the first way that I normally use, which is you look at the outermost part and then you move toward the inside. Okay, you move toward the deepest part. So now remember, like implicit differentiation, you take the derivative of both sides. Yeah, so y prime equal the derivative of this, thing. You have to look at, remember, matching the rule first. So it's a good idea to have a sheet of rules. And just let you know that since the derivative rules for the inverse function are pretty complicated, so I didn't type it in here. But it's good to have all the rules on a paper or however you want. You can go through on the internet and print them out. Like there's so much of them on the internet. So so right now we look at, again, it's not a constant. It's not just something. Oh, something to the power. Bam. See that, something to the power? So we found a root. So something to the power, remember, you just bring down the power to the something, and the power minus 1. So in this case, -7 minus 1 becomes -8. So now you ask yourself, alright, since we take one derivative already, and are we done? Look back at the problem. Not yet, because we have just been taking the derivative of something to the power, but there's also something inside here that we haven't taken the derivative of. So now we will take a look at this and we'll match them with the rules, alright? Match them with the rules. So we will see if we can find something that looks like 1 minus x over 7. Let's look here. We have constant. We have this power. Definitely not that one. E to that, definitely not. And then after you go through all of them, you find that, yeah, nothing really look like 1 minus, x to the 7, right? So you go back to the question and think, wow, can I rewrite this expression? Maybe can I rewrite it in a different way, and then so I can be able to find the root. So if you rewrite it, you will see that this here, x over 7, you can actually rewrite it as 1 over 7 times x. It's the same thing, right? Remember, because if 1 over 7 times x is just x over 7. So now after you rewrite, you see, oh wait, isn't this looks like one of the root? See, something like see here, there's something and the x is right here. So now you know that to take the derivative of this is just equal to 1 over 7, right? 1 over 7, but it's negative because don't forget the negative side. And derivative of 1 is just 0, so it doesn't matter. So okay, so now what are we going to do with this negative 1 over 7? Remember, we just multiply this derivative back into the derivative that you just found. So at the end, you find that the answer is just actually this. Hope I didn't make a mistake, because a negative times the negative is become positive and the 7 cancel out. So hopefully your answer will become this. Okay, now use the other approach I talked about from the inside to the outside. Okay, same question. Y equal 1 plus x over 7 to the negative 7 power. And we draw those parentheses again to try to find the parts. Okay, now look at the most inside part. The most inside part of it looks like the last question in just 1 plus, right, x over 7, and the outer part is just something to the power, which is just 1 plus x over 7 to a power. So then you would just take the derivative of each of them and multiply them together. It's the same thing, but so let's do a more complicated example right now. Okay, and now let's do a question that I picked from somewhere else, not from the book, maybe from the book, I'm not sure. Okay, this question is this: is y equal radical cosine, cosine of tangent square x. Whoa, this looks pretty complicated, right? Nah, it's not. It's a piece of cake if you know all the rules pretty well. Okay, first let's again use the way that I usually do to solve this problem first. First, take derivative of both sides, y prime. So this derivative, now when you look here, right? We will go to the document that has all the rules and matching the rule versus matching them. See if there's any rule that give us that looks like square root of something. Look here, we have constant here, we have just u here, we have u to the power here, e to the power, a to the power, and ln u, and those are just all the trig derivatives. So now we didn't find any rules that match this expression, right? So the next step that we do, we think about, okay, can we rewrite this expression so we can find a rule that match this one? So, and remember, anything to the square root is, we can write it in as to the power, right? So it's cosine of tangent square x to the 1/2 power. That is same thing as saying that we're taking the square root of this thing here. So now, since after we rewrite that, we go back to the sheet again and look through the sheet, and we found the power roots again. So after that, we we write it as, remember, it's 1/2. It's 1/2 of this cosine of tangent square x, and this will be 1/2 minus what? Remember 1, right? So it's 1/2 minus 2/2, which give you a negative 1/2. So to the negative 1/2 power. So now again, we already take the derivative of the outermost part. Now we just move in. We'll ignore the square root. We'll ignore the square root for now because we already took the derivative of the square root. Now we look the inside. What is the next layer of this expression? We can see the next layer is cosine of something. See that? Oops, sorry. Next layer is the cosine of something. So since now we know the cosine of something, we'll go to our the sheet to find the derivative of the cosine of something, in which is negative sine something. So the next derivative of this thing is negative sine of something, right? And remember that something here is tangent square x. So write it in complete form, which is just negative sine of tangent square x. So right here, this is the derivative of this cosine of tangent square x here. So what do we do with that? Remember, we just multiply these things with the derivative that we just found before. So let me open another one real quick. Hello? Okay, alright. So let's rewrite the problem here. The derivative was 1/2 of cosine of tangent square x to the negative 1/2 power, right? And then now we will multiply negative sine tangent square x into here. Okay, so now we look back into the original question. After we finish taking the derivative of this cosine u here, is there anything else inside this? It is the cosine of something, the most inner part of this expression. And when we look at that, we find it's no, because there's another thing here, tangent square x, right? Tangent square x. So the next level is going to be tangent square x. We have to take derivative of that. And so we look at tangent square x next. Tangent square x. So tangent square x. We'll look at the sheet again to match all the rules here to find if there's any rules for tangent square x. And we find there's nothing. There's tangent u, right? But there's no tangent square u. So we'll look back here again and see, can we rewrite this? And the question is the answer is yes, because remember the tangent square x is really tangent x square, because you're squaring the ratio. So now take a look at this and look back there. If you look back at the sheet, you'll find that this matches the power rule. So which means the derivative of this will be power rule, which means just 2, right? Bring down the power to tangent x to the power of 1, because 2 minus 1, right? So So now look back at the original question again. We have already been taking the derivative of the square root, taking the derivative of cosine something, and taking the derivative of tangent x to the power. Okay, is there anything else that we found the most inner part of this expression yet? The question is, nope, there's still one more thing here, which is the tangent x, right? The tangent x here, because we only been taking the power of that, but haven't deal with the tangent x yet. So we'll just again look at the rules, but it would be a good thing if you memorize the rules already, and so you don't have to look at the sheet. Okay, and so you remember that the derivative of tangent x, it's secant square x. Alright, so yes, so that will be your most inner part. Like, this will be the answer of your question. This will be the answer. You can simplify them, but you may not need to. It depends on what your professor say. You may not need to simplify them. Yep. So you just multiply all the derivative together. And when you look back at the question, you may think that, oh hey, there's like tangent x is not the most inner part. The most inner part of this expression, because shouldn't that x be the most inner part? Because, right, tangent of something, so that means x is that something. But remember that the derivative of x is just 1, so it doesn't really make a difference. So that's why the most inner part here, the most inner part of this question is tangent x. Yeah. Okay, so hopefully this will help. And one last thing before I end this video. I talked about the derivative rules for the trig function, for all the trig function, and then I also will talk about the derivative rules of all the inverse trig function. And one really good trick to remember, like to memorize those derivative of those trig function, is that if you're taking the derivative of any trig function or inverse trig function that start with a c, like cosine, cosecant, cotangent, the answer always start with a negative sign. Always start with negative signs. So yeah, just keep that in mind, and hopefully I didn't confuse you. Oh wait, you know what? Okay. I guess we should. Let's do a quick way to remember the second way to take the derivative. So let's do that really quick. Okay, that was the original question. Now remember the parenthesis way, you're moving from the inside to the outside. So if you're moving from the inside, you find that, right, x is the most inner part. So you find x, and then you find that there is tangent x, and then you find that there is tangent x square, and another part, it's cosine to the something, which is cosine to the tangent square x. So what happened is, you remember, you just take the derivative of each part and then you multiply them together at the end. Yeah, this is just a matter of style, like whatever style you want. Like I do that from the outside to the inside, but you can also do this from the inside to the outside if you think this is easier to see, because some people find it hard to find like what is really the expression, what the expression is. Like they find it hard to break the expression apart when they break it from the outside to the inside. Like a lot of people find that it's easier if you look at the simplest part first, and then you build it from the outside. I mean, from the inside. So, and you may not. I didn't wait for you to write down the answer. So, here's the question again. It was cosine and tangent square x, and then the answer for this is 1/2 alright, is 1/2 this times, or actually no, hold on, it's 1/2 this times the cosine of tangent square x to the negative 1/2 power, and times negative sine of tangent square x times 2 tangent x times secant x and tangent x. Okay, if I made a mistake here, you can always correct me and slap me in the face next time, but hopefully this is the right answer. So yeah, you can use some time to copy this question down, and you can do it by yourself again without, and see if you can get the same answer. So alright, hopefully this helped.